Does Planet 9 exist? That's the question most people start with, and it's the wrong one. The right question is harder and more interesting, and it reaches beyond astronomy into how science decides something is real. 6 objects at the outer edge of the solar system, trans-Neptunian objects in the Kuiper Belt, have orbits clustered in a way that shouldn't happen by chance. Their orbital planes tilt similarly. Their closest approaches to the Sun group in the same region of space. Scatter objects randomly in the outer solar system, and the probability of this alignment occurring without an external cause is less than 1%. That number comes from the original analysis, and it's disputed, as we'll see. But it was enough to launch a hypothesis. Something is shaping those orbits. In 2016, Konstantin Batygin and Mike Brown at Caltech proposed the explanation: a planet. Roughly 5 to 10 times the mass of Earth, orbiting the Sun at a distance far beyond Neptune, originally estimated at 400 to 800 astronomical units. That estimate has been refined since. In 2021, it narrowed to around 380 astronomical units. In 2025, the best fit dropped further to roughly 290, an orbital period measured in thousands of years. Too far and too dim for existing surveys, but massive enough to sculpt the orbits of smaller objects across the outer solar system. The model is elegant. It explains the clustering. It predicts that certain populations should have orbits perpendicular to the ecliptic plane, and those objects exist. It accounts for a puzzling tilt in the Sun's spin axis. Multiple independent lines of evidence point to the same solution, and the evidence has kept building. In 2024, Batygin and Brown published new work focused on a different population, low-inclination trans-Neptunian objects that cross Neptune's orbit on long, looping paths. Simulations showed these objects can only make their way past Neptune if a distant massive planet is there to slingshot them inward. Without Planet 9 in the model, the galactic tide alone is too weak. With it, the distribution matches observation. Then came Ammonite. In mid-2025, astronomers using the Subaru telescope announced the discovery of a new object, the fourth member of the Sednoids, a rare class of bodies with extremely elongated orbits. What made Ammonite significant? Its perihelion direction lies opposite the other known Sednoids, filling a gap in the orbital distribution that had been unexplained. Simulations showed its orbit remains stable over the full age of the solar system, but only if a distant planet exists well beyond 500 astronomical units. And in early 2025, something more provocative. A team comparing infrared sky survey data from 2 space telescopes, IRIS in 1983 and Akari in 2006, found an object that appeared in one position in the older data and in a different position in the newer data. The displacement was consistent with the slow motion of a distant, massive body over 23 years. Exactly what Planet 9 would look like, a faint source drifting imperceptibly across the sky. The detection hasn't been confirmed in more recent imagery, but if it holds, it could be the first direct sighting. Each new piece of evidence strengthens the case. Each one narrows the parameter space. On paper, this is compelling. If this were a court case, the circumstantial evidence would be strong enough to take seriously. But here's where it gets complicated. Because this exact pattern, strong mathematical prediction, multiple supporting observations, growing consensus around an unseen object, has happened before, and last time, the planet wasn't there. 1846. Urbain Le Verrier noticed that Uranus wasn't where Newton's equations said it should be. Systematic deviations, something unseen pulling on it. Le Verrier calculated where a hypothetical planet would need to be to produce those exact perturbations. He sent his prediction to the Berlin Observatory. Johann Galle pointed the telescope at the predicted coordinates. Neptune was there, within 1 degree, one of the most triumphant moments in the history of science. A planet discovered by mathematics before a human eye ever saw it. 13 years later, Le Verrier applied the same method to Mercury. The innermost planet's orbit had a small but real anomaly, its perihelion precessing faster than Newtonian mechanics predicted. Le Verrier proposed an unseen planet, Vulcan, orbiting between Mercury and the Sun. The math was clean. The prediction was specific. For the next half-century, astronomers searched. Some claimed to have seen it, dark spots crossing the face of the sun during transits. Reports appeared in journals. The scientific establishment largely accepted that something was there. Vulcan was never found. The anomaly in Mercury's orbit was real, but the explanation was wrong. The actual answer came in 1915, when Einstein showed that space-time curvature near a massive body produces exactly the observed precession. The math that predicted Vulcan was correct within its framework, but the framework itself was an approximation of something deeper. Newton's gravity was incomplete, and Mercury's orbit was the first place that incompleteness became visible. Think about what that means. For over 50 years, rigorous mathematics said a planet should exist. Observations were claimed. The prediction was taken seriously by the best minds in the field. And the planet wasn't there, not because the math was bad, but because the physics underneath was an approximation of reality that nobody had yet improved on. If you're inclined to trust Planet 9 because the math is strong, and the math is strong, then Vulcan is the case you need to sit with, because the math for Vulcan was equally strong. The difference wasn't quality of analysis. It was that one prediction lived inside a complete theory, and the other inside an incomplete one. And from the inside, they looked identical. Now, is Planet 9 the same situation as Vulcan? Not necessarily. The evidence comes from multiple independent object populations, not a single orbital anomaly. Nobody is claiming a direct detection. But in both cases, gravitational anomalies point to an unseen mass. The math is self-consistent, and there are alternative explanations that don't require a new planet. Some researchers argue the orbital clustering is an artifact of observational bias. Samantha Lawler at the University of Regina has been vocal about this. Surveys have looked at certain parts of the sky more carefully than others, and the clustering may dissolve when detection biases are corrected. A survey she co-authored found no statistically significant clustering once selection effects were accounted for. Others propose that the gravitational effect comes not from a single planet, but from the collective mass of many smaller objects in the outer solar system. Still others, cautiously, suggest modified gravity at extreme distances. This is speculative, and not the mainstream view, but it echoes the Vulcan lesson directly. Sometimes the answer isn't a new object. Sometimes it's new physics. HALE wasn't looking for a pattern in the naming when this video started taking shape, but it showed up anyway. Neptune was predicted and found, so the method was trusted. Vulcan was predicted and not found, but by then, the trust in the method had outlived the evidence. Planet 9 sits in the space between those two outcomes, and the name itself, quote, 0, not, quote, 1, nudges the conversation toward existence before the telescope has weighed in. Once something has a name that implies it's a planet, the question shifts from, does the evidence support a massive body, to, where is Planet 9? The assumption gets baked into the language. The telescope that may settle this is already running. The Vera Rubin Observatory in Chile, an 8.4-meter mirror and the largest digital camera ever built for astronomy, has begun survey operations. It will photograph the entire visible southern sky every few nights, building sensitivity over time to objects too faint for any single exposure. Planet 9, at its predicted brightness and distance, falls within Vera Rubin's capability. Brown has said it plainly. If something is moving at 500 to 600 astronomical units, this telescope will find it. If you're watching this in 2026, you're watching during the window when this question gets answered. The data is being collected now. Somewhere in Chile, a camera is scanning the sky, and every few nights, another layer of depth accumulates. If Planet 9 is where the models say, and at the brightness the models predict, Vera Rubin will see it, not as a dramatic announcement, but as a faint dot that shifts slightly between exposures. And if it surveys the predicted region and finds nothing, the hypothesis doesn't just die. Either the orbital parameters need adjusting again, pushing the planet further out or into a less favorable part of its orbit, or the explanation is something else entirely. Each year without a confirmed detection raises the cost of belief. Each adjustment to the prediction, after the fact, weakens the analogy with Neptune and strengthens the analogy with Vulcan. There's a psychological dimension here, but Teagan and Brown called it quote 4, not quote 5. That naming matters. Once something has a name that implies it's a planet, the public conversation, and to some extent the scientific one, shifts from, does the evidence support a massive body, to, where is Planet 9? The assumption gets baked into the language. And that makes the alternative explanations harder to discuss, without sounding like you're being contrarian. So the question isn't, does Planet 9 exist? It's this: when does a mathematical model earn the right to be called a discovery? Neptune says, when the telescope confirms it. Vulcan says, not before. And right now, Planet 9 lives between those two precedents, too well supported to dismiss, too unobserved to confirm. A prediction waiting for a photon. That tension between what a model promises and what instruments can verify doesn't stay in astronomy. It shows up everywhere that confidence outpaces evidence. And it shows up in a very specific way when someone reverses course on a promise that millions of people took seriously and replaces it with a new promise that sounds just as confident. The physics of lunar settlement is real. The timeline attached to it, that's a different kind of question. And it deserves the same scrutiny we'd give a planet that exists only in equations.